is equal no on the button you added earlier to prevent button bounce. I'm guessing you mean there's for buttons there is a button bounce. I think you're referring to when you press the button and it kind of oscillates and causes multiple button presses to be heard. And you can do that hardware-wise, you can fix that, or you can just do it software. Basically make it so that in the software, when you're coding, that after pressing the button, it can't listen to a button bounce for some odd amount of time, maybe like 0.1 seconds. And that can fix the problem of button bouncing without having to do a hardware fix. Okay, so we have these connected as they have here. We still need this 0.1 UF, and then we have these TX RX pins, which we're going to be getting to. So TX and RX are basically how the USB UART connects to the Atmega chip. So let's move back over to here, and first let's add the capacitor for that. So we can just copy paste this. And add a ground. So ground. So now we have this done, and what we're left with are the communicator pins. Let's also add the capacitor over here since we're at it. So we see a ground and the VCC tag. So now we have our filter capacitors. Okay, so for communication, the way that the Atmega chip works is that they have these TX and RX pins, which if we go to this picture, we can see our pin 1 and pin 0, or PD1 and PD0. We're going to be using that to connect to the pins over here. So let's add some tags. So TX, which can connect to PD1, and RX, which can connect to PD0. And one thing not to mess up is that for the where we're going to be connecting it on the USB UART, we're not going to be connecting to the RX tag to the RX on here, because the transmitting information goes to the RX pin and the receiving information comes from this transmit pin. So we got to make sure that those are done correctly, such as this. So let's add that. We're still missing one last pin. That's the DTR. So what DTR does, it's data transmit ready, and what it does is that when the Atmega chip is pulling in the information, it does this reset. It pulls itself low and resets it, and then the information comes in. So what we do is that we add we're going to be connecting this to the reset pin of the Atmega, and we can do that now. So let's first add the tag over here. We can just say reset. And connect this to here. So now we have that. And for when you're doing these connections, you also want to have a capacitor between them. Similar to, it's a different type. It's not a it's in a way a filter. So we can just add a capacitor between the communication. So we can see that if we go back to here, reset has this capacitor connected to DTR. That's what this is. And we're going to be getting to this pull-up resistor in a moment. So this reset, we can connect over here to the DTR pin, and we can add a capacitor. and the standard is 0.1 UF. We've been using a lot of those. Okay, so we saw in that picture they have this pull-up resistor. So we mentioned a pull-down, and pull-up works the same way except in the opposite. So we see this line pulled over reset. That basically means that normally it should be high at 5 volts, and at low is when something happens. In this case, it's the reset when information is being transferred. So we want to add a resistor to do that. So similar to the resistor below, we're going to want to have a high value because we don't want much current to be flowing through here. We just want enough that the this will always be seen as high. So we can just add that resistor. Okay, so now we have the setup for the Mega chip. We skipped the external oscillator because we're just going to be using the internal clock. We've added the button LED, the capacitors, and the way to communicate with the FT pin. We've added all the capacitors here for all the pins, connected the grounds to ground. Added the ferrite bead and made sure that VCC is connected to the actual power. Okay, so now we're going to be shifting over to we have to basically apply the footprints that we're going to be using to these schematics. So we can click on here, this button. This is just annotates it. And it basically brings up this window for picking the footprints that you're going to be using for these parts. And it shows all the parts that you have. So we see all of these. These are the libraries. So for instance, the capacitor one is right here. We're using SMD. And it shows all the possible capacitors that you can use. So as I mentioned before, we don't really want to go below 0805, which is the 2 millimeters by 1 millimeter, because it'll be very difficult to solder for hand soldering unless you have a lot of experience. Even 0805 might be a bit small for novices. So we'll add this one. This adds a longer pad to make it easier for hand soldering. You can just add these for all of the capacitors. In some cases, depending on the capacitor you can find, you might have to do a bigger one. 0805 is very common, but yeah. So then we want to add an LED. So we can just scroll down to LED. 0805. That was the size that we picked earlier. So we can just add that. This ferrite bead was one of the parts that I added, but you can do the same thing on SnapEDA to basically find the part for this. So the one that I used was by the name of this int. So we can add that. So USB micro, if we go to connectors, we see that there's this connector USB. We can go down to the micro ones and we can just add the Molex right here. This will be the part number that you'll be using for when you look up the connector that you want to use. So resistors, we do the same thing. We can go down to resistor and add the surface mounted ones and go to 0805 with the hand soldering. Add those in. And then the ones that we added, and along with the ones that have preset ones, like the Mega and the FT, are automatically done, so we don't have to worry about that. So now we've added all the footprints to our schematics, and we're done. Now we can move over to the circuit board layout. So we press this button, and we see this large square where we're going to be working. So if we want to get our parts in, what we do is we go to Tools, and we update PCB from Schematic. So this will basically bring all the parts that we just added in, and now we have them here. So in order to add the outline, we basically go to this graphic polygon, graphic lines, and we can basically just make we can do a basic square. So we can just make a square. This will be much larger than you might need for something of this amount, but we can just connect these, and we basically have our outline for our board. So the next step, what we're going to be doing is you basically have to position your parts in the best possible arrangement. Sometimes this can take a decent amount of time. You're basically trying to limit these lines. So these lines are what we made in our schematic. It's basically these connections. And we want to limit the crossover between them. So this can take a while, so I just have a pre-done one. So we can X out of here, we can save this. And I'll load up the unnested one. So if we go to this no nest, I basically have it so most of the lines have not been are not crossing, but we still have to do the traces. So the traces are the actual connections between the parts, and we're going to be starting with that. So one of the things that most boards usually have are something called a ground layer. So we have this ground that we mentioned in our schematic, and in order to simplify connections, what you do is you add this ground layer. So it's basically a covering that will connect all the traces that are connected to ground. So you can do this add filled zones, click, and you see this ground, and we're adding it to the top. So let's add this, and we basically just surround our board. For the case of this PCB, we're just using a two layers is in top and bottom. You can go up more than 16 layers, but it gets progressively more expensive. And most times you don't, especially for something this simple, you won't need that. You might even be able to do one layer. But for the purpose of two layers, we'll add a ground layer to both sides of the board. So let's do that. And I can fix that where it started after. Okay, so now we have this. Okay, so as you can see, some of the lines disappeared. Some of the grounds are still there. What that means is that the grounds are not connected to each other, and so all grounds have to be connected. So we have this thing called a via. What a via does is it's basically a tiny hole that you add to your board, and you can use it to connect layers. So we see that this ground says they're not connected. That's because this ground here is separated from this ground. So we can just add a via, something here. And most times this will just connect those layers. So let's first start with the, we'll get back to that. Let's start with the traces. So let's add a trace. So we can click on this line, and we have it set up to be working on the front layer, which is where all these parts are. And we can just connect this. KiCad's nice in which that it shows exactly where you're trying to connect, and it won't let you connect to something you can't to, such as this. So let's connect it to here. Connect this to here. Do that. So then we have this VBus. VBus is what we, the pins that we did connecting to the VBus pin of the USB. Let's connect those. So we have this VBus. Here, connect this. Let's do this. In most cases, you want to avoid right angles, 90 degrees, and just try to do 45s wherever you can. This is more important in things like radio frequency transmitters, where 90 degrees can cause a lot of noise in the signal, but it's good practice to keep it. So we see that we need to connect this VBus up to here. So let's do that. We can just move this part maybe slightly to the right. Let's do a connection, a trace. So now we have this connection here. we have these reset pins, which we can connect together to this reset. And we have this RX and TX. So we want to make sure that we don't, we connect this pin to here. That's the DTR pin. We want to make sure that we can connect the RX and TX together. So if we see what we caused here is that if we try to use this RX, we can't get to it now, which is just, it's not good. So what that means is that we have to change how this trace works. So let's get rid of the one that we did. And redo it. So we saw that because we did it here, we basically cut off this pin. So let's instead make this pin go around. Like that. So now we have this RX and it can connect to here. And our TX can connect as well. Oop. So now we have that. We still have to do this VBus. Let's connect that to this VBus. So now we have mostly the things on the bottom here. So we see the 3 VBuses here. We can connect those together. This VBus up here can just connect down. These pins all connect together, so let's do that. Okay, so now we have to these 2, and we see that they cross, which means they're going to be kind of difficult to add, but not impossible. So in order to make this work so that we're not blocking this pin on the right, let's go around. So we want to make sure that we're kind of keeping the right angles. And by doing that, we have this connection. In most cases, for the TX and RX, you want to try to keep the how they're shaped, the traces, to roughly the same shape. So let's do the same thing. Let's just kind of go and follow it. That's because we're mentioning the whole shape and length. We're mentioning the whole sine waves, and as the sine waves are taken in as information together, we want to keep them roughly the same. The time it takes to go through the trace roughly the same. So then we have this pin left. Up here, we see that these grounds don't seem to be connected, but we can add a ground here. It doesn't seem to be. Add a ground here. Right there. So just add these grounds. These grounds have to be connected. And we just have this VBus left. So we don't want to connect this. Why don't we just bring it down like this? So we still have 7 unrouted. So that's over here. So let's add the connections for here. This to this. The grounds have to be connected. So we can just do that. We have 1 left. So we can just add a ground pin. Okay, so what this is saying is that the grounds are not connected. So let's just add something here to connect them. Okay, so now we have 0 unrouted traces, which basically means we've wired up the entire board. So we can take a view of what it looks like. Here we see that it shows all the parts. We can see all the most cases the interesting usually shows the traces going between them. And what we do now is that we have our PCB done. If we want to send this to a company to basically make it, what we do is that we go to this file, plot, and we get these layers, which are basically layers on the board. This creates files, and we can use these files to basically have them make the PCB. So that is basically a simple version of a schematic and a board, which you can do, and how to use the software. I didn't go into some things like via sizes, which you can change, basically the size of these holes, trace sizes, which are the sizes of these traces. For traces, you want to, for anything low power, such as the Atmega and Arduino, you can basically keep the traces to what they standard are, 0.25. But if you're trying to do something with high power, so like if you're connecting it to a going upwards to like 10 amps, increasing the current to much larger than anything that you'd have here, so like power systems, you have to basically widen the traces. You can change that here. That's done to make sure that the traces can handle the amount of current that are going through the system. Okay, so that is it. I will change this back to the picture.